Hi, I'm Antoni Navarro, a PhD student at Barcelona Supercomputing Center, and I'm here to talk about our work, enhancing resource management through prediction policies. This is the outline of our presentation. I'll briefly begin by introducing what motivated this work and our objectives, which are comprised of a monitoring infrastructure and prediction-based policies. After that, we'll talk about the performance evaluation of our work, and I'll give some concluding remarks and future work. Current HPC systems have evolved and now include complex memory hierarchies and complex technologies. And this is partly due to real applications also evolving and needing more efficient tools. Task-based parallel programming models at the same time have emerged as an alternative to increase productivity on these applications. And these parallel programming models usually rely on runtime systems that cope with the system complexity in a transparent manner. Resource managing policies in these runtime systems either focus on one of the two aspects, which is performance or energy, rarely both. With that said, our aim is to tackle both of these aspects, energy efficiency and performance. And we will do this by creating resource managing policies that are based on predictions, so that runtime systems can adapt the execution to the underlying parallelism of an application. To do this, we need two things. First, a monitoring infrastructure that is capable of providing our runtime systems with the information we need, which is the current amount of workload in the system. And two, policies that use these predictions in order to ensure that the active number of CPUs at all times is enough in performance aspects, but doesn't exceed energy efficiency aspects. In order to understand how resource management policies work, I'll base my explanation on this example, in which we can see the timeline of an application with two computational phases. In phase alpha, or the first phase, there's enough work for 6 CPUs, and in phase beta, there's enough work for 4.5 CPUs. Marked as blue, we have the required number of CPUs at all times in both phases. And marked as red, we will see the active number of CPUs with the policy we're talking about. In this case, we're talking about the performance policies. And these prioritize performance by being greedy in terms of resources. So idle threads consume processor cycles instead of yielding the processor. What we can see then is that all CPUs are used at all times, and the area between the blue and red series could be area that we are saving in terms of energy. On the other hand, we have policies that take into account energy efficiency. And in these, the idle threads yield the processor in order to minimize energy consumption. However, they're very reactive to runtime aspects. So as soon as work is added or subtracted from the schedulers of runtime systems, the change in active number of CPUs is very reactive, as we can see in phase beta of this example. There have also been hybrid approaches that try to tackle both challenges, performance and energy efficiency. These are based on policies that switch between performance policies and energy policies depending on a threshold. However, they are too naive to cope with both aspects. So we advocate for this or our prediction-based policies, which are capable of adapting to the workload of a system. To do this, we need a monitoring infrastructure, which pinpoints critical changes in tasks, threads, or CPUs. So in the application code, we annotate with directives units of work. In the runtime code, we create these tasks, but prior to that, we notify the monitoring module that we're creating a task. In the case of the runtime, the monitoring module detects the task's type and infers the expected cost or computational weight of this task, which is then fed to the prediction module, which aggregates these predictions and passes them to the CPU manager or our resource management policies. A very important part of this monitoring infrastructure is the addition of the cost clause, which was introduced in previous work. The cost clause is user giving information about the computational weight of a task. This information is already known by users, and it allows to normalize metrics such as the execution time of tasks. By normalizing these, we can obtain unitary metrics like time per cost, which can then be passed to an exponential moving average to adapt to changes over time. These metrics are then used with future tasks cost in order to predict metrics such as the prediction of time. With this aggregation of cost or workload, we can then predict the optimal number of CPUs, and then our policy is based into actions when threads poll for tasks or add tasks to the scheduler. If a thread polls for tasks and no more tasks are available, we compare the optimal number of CPUs to the current one. If the current number of CPUs exceeds, we can simply yield the thread, the CPU. If it doesn't, we simply keep polling for tasks. As for the other action, when threads add tasks to the scheduler, we check if the current number of active CPUs is enough for the demand. If it is not, we can resume as many CPUs as we need. In order to evaluate our policies, we used 6 scenarios: Cholesky, Multi-Saxby, Gauss-Seidel, and HPCCG, and 2 of them, Cholesky and Multi-Saxby, with fine and coarse-grained task scenarios. We evaluated 2 architectures, Manycore 4 and KNL, and 4 runtimes: libcomp, Intel OpenMP, OMS2 with linear regions dependency system, and OMS2 with discrete dependency system. And we evaluated both of these for OMS2 due to the discrete one having less overhead and being much faster. We also solely target our work on single node, but this could be extrapolated easily to multi-node. And for other runtimes, we tested all the available resource management policies, which are passive, active, and hybrid in the case of OpenMP, and idle, busy, and prediction in the case of OMS2. We also group them as shown due to their similarities. In the case of Cholesky coarse-grained and for all plots, we will see that the normalized performance is shown, which is the performance of all scenarios normalized to the best scenario, which in this case is the OMS2 discrete dependency system prediction policy. For KNL, we can see how it is also almost similar to the best scenario. In the case of fine-grained Cholesky, we can see that the prediction policy yields similar performance. However, this led us to find that the monitoring module adds slightly more overhead in the discrete dependency system due to its contention being minimal in the dependency system. In the case of Gauss-Seidel and HPCCG, we can see how the prediction policy in both OMS2 versions for all scenarios yields similar performance when compared to OMS2 linear version. And it yields either similar performance or surpasses all other performance in both scenarios. In the case of Multi-Saxby coarse-grained, we can see how the busy policy yields better performance than the prediction one. And in the case of fine-grained Multi-Saxby, we can see that comparing all the OMS2 policies, our policy yields similar performance in KNL or surpasses all other policies in Manycore 4. In the case of coarse-grained Multi-Saxby, we attribute these changes to the accuracy of predictions, which could be enhanced if we also took into account other metrics, since it is a memory-bound benchmark. To evaluate energy aspects in our policies, we use the energy delay product or EDP metric, which relates energy to time. Thus, in these results, we are showing that lower results are better results. In the case of coarse-grained Cholesky, we can see that prediction policies obtain better results than any other policy in Manycore 4. And in the case of KNL, the only configuration that beats our prediction policy of OMS2 discrete is OMS2 linear idle policy. In the case of fine-grained Cholesky, we can see that OMS2 discrete prediction policy yield less EDP than any other policy for both architectures, except when compared to GOM's passive policy in KNL. In the case of Gauss-Seidel and HPCCG, We can clearly see how prediction policies beat any other policy in any implementation and architecture. For the multi-XP variant, of course, we can see that EDP results in KNL are very similar across policies and implementations. However, in Mare Nostrum 4, we can see that prediction policies achieve considerably lower EDP than any other policy, except when compared to GOM's hybrid policy, which are similar. Finally, both for the fine-grained multi-XP scenario, we can almost see similarities across all policies, with the discrete one being the most performant in EDP in Mare Nostrum 4. And for the coarse and fine-grained scenarios in multi-XP, we can see how predictions benefit from fine-grained and irregular applications, especially in Mare Nostrum 4 prediction policies, since they beat any other policy in EDP. In order to evaluate further our prediction policies, we tested sharing of resources with prediction-based policies. Dynamic load balancing, or DLB, is a library that allows to share resources between processes. This helps to react to different sources of imbalance. An example is shown next, which targets one single node with two applications using DLB. As we can see, there's one process, red, using CPU 0 and 1, and process 2 is using CPU 2 and CPU 3. Process 1 has gaps which could be filled by process 2. So by using DLB, we can share resources among these processes and turn this timeline into this one, where the second process benefits from the first one at the beginning, and process 1 benefits from the second one at the end, effectively turning our usage timeline much shorter. Combining all DLB and prediction-based policies is as simple as when threads are to be idled, which lend their resources instead of yielding them. And when a phase of high parallelism is detected, more resources can be acquired from other processes. In order to further evaluate our policies, we used two applications, Gauss-Seidel and Stream, and we executed them in a single node while sharing their CPUs. So each of these CPUs uses half a node of CPUs. We executed single and concurrent versions first to see if there would be cache pollution effects, and we saw no negative effect. So then we executed the concurrent both applications with the DLB lend one idle policy, which is the default policy of DLB. We saw that while one application could clearly benefit from it, the other one increased its execution time, which we attributed to the amount of calls to DLB. We tried to fix this by using a slightly better approach, which is the DLB hybrid policy, which spins for a while before lending processes. But we saw no particular benefit from this, because the amount of calls remains the same. We then tried the DLB predictive policy, which is the DLB mode with our prediction policy. And we saw that while one application did not reduce or increase its execution time by much, the other one could clearly benefit a lot from it. We partly attribute this due to the reduced amount of third-party library calls, since our prediction policy can target and predict the amount of workload and not be as reactive as the hybrid one. In here we can see two traces of execution which are not related to the table above, where we can see the hybrid and prediction policies in play. As we can see, for both applications there's a considerable reduce of overhead, and we can see how the sharing of resources is done in much more compact chunks than in the hybrid policy. In conclusion, our prediction policies maintain performance while improving energy efficiency, and as we've just seen, in the prediction-based sharing of resources, we can enhance both performance and energy efficiency. Out of this work is task characterization in order to improve scenarios like the multi-XP one, in which we could characterize tasks and detect memory-bound tasks or applications. This concludes our presentation, and if you have any doubts, we'll be happy to answer them either by mail or during the live session. Thank you.